Hello, everyone, and welcome to today's training on EPA's spreadsheet tool for estimating pollutant loads, or STEPL for short. For those of you that don't know me, I'm Colin Geisnoffer, and I work in EPA's Region 5 office in Chicago, and I'm currently EPA's lead for STEPL development. Today's training will be a little bit different than past trainings and will include a brief overview of STEPL, followed by a detailed walkthrough of the model and BMP calculator tool for a mock watershed. If you're interested in specifics related to the tool's use and functionality, I encourage you all to visit our STEPL webpage where you can find previous trainings that cover those areas. Before we get started, I'd like to cover some of the webinar logistics. First, if you're experiencing any technical issues, please use the questions widget on the right side of your screen and our GoToWebinar expert will respond and try and squash any bugs you're having. That same questions widget can be used for any questions about the model throughout the course of the presentation, and we'll attempt to answer them as they're submitted. Additionally, throughout the presentation, there will be pauses for question and answer sessions. This was originally intended to be live, but due to the overwhelming interest in this training, instead my colleague Don Way from EPA HQ will dutifully compile your questions, passing along any recurring questions to the presenters at this time. So if your questions aren't answered, make sure to blame Don and not me. This webinar, along with relevant input data for the mock watershed, will be archived for later viewing on EPA's STEPL website. This same website has a link to STEPL's help desk, which I encourage you to use if you have any STEPL related questions or having any issues running your model. There's also a STEPL listserv that I welcome you all to join if you're not already members. And we will be sending an email out to you after this presentation with a brief survey, a link to EPA STEPL webpage, and information on how to join the listserv. So look forward to getting that, hopefully sometime here in the near future. Lastly, the materials in this webinar have been reviewed by EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of EPA. Any mention of commercial enterprises, products, or publications does not mean that EPA endorses them. And with that, I'd like to introduce today's speakers. Aileen Malloy and Mustafa Fazulaboy are both with Tetra Tech on contract to EPA for model development and support. Ms. Malloy is an environmental scientist with a wide array of experience and expertise in the areas of watershed management and planning, stormwater management, TMDL development, BMP implementation strategies, and load reduction analysis. She currently serves as Tetra Tech's project manager for EPA's STEPL support contract. Mr. Fazulaboy is a water resource environmental engineer with experience and expertise in water quality modeling, hydraulic modeling, and stormwater management planning and design. He specializes in the fields of hydrodynamic modeling, surface water quality modeling, pollutant transport, as well as data analysis and statistics. His STEPL role is as a modeling technical expert. Okay, with all that out of the way, I'm going to turn it over to our presenters now.
Thanks, Colin. This is Aileen. So to quickly summarize what we're going to be covering today, this training is focused on the new STEPL users, folks that haven't had experience with it before. If we have any experienced users, that's great. You might learn some tips and tricks too. But we're going to go over a basic overview of STEPL. We'll talk about navigating the worksheets and walk through a real-time example of the basic inputs and outputs. We'll also show examples of how to use the more advanced input worksheets, tools, and calculators that can be used for more complex scenarios. And we'll discuss adding and modifying BMPs. We'll be using the 10 watersheds template, which is available to download directly from the EPA STEPL website. This version does not require the installation of the STEPL setup program and comes pre-formatted with space for 10 watersheds. So what is STEPL? STEPL stands for, as Colin mentioned, the spreadsheet tool for estimating pollutant loads. It's an EPA model based on a customized Excel spreadsheet that supports planning level decision making. It's designed to help determine annual average pollutant loadings from non-point sources and estimate BMP effectiveness at reducing pollutant loads. STEPL calculates nutrient and sediment loads by land use type, by watershed, and calculates load reductions from BMPs based on efficiency values. STEPL was designed to be easy to use and comes with a significant number of default parameter values to make its use simple. If a user has information to substitute for the default values, this can be done without any additional programming knowledge. So STEPL was originally developed to assist state non-point source project managers report their load reductions from local water quality improvement projects to EPA. This data was entered into EPA's Grants Reporting and Tracking System, also known as GRITS. And while it's still used for this purpose, STEPL is also used by other federal, state, and local partners, consultants, researchers, etc. STEPL is best used as a non-point source project planning and results estimation tool. So we're going to go into some of the overview information about STEPL, and then we'll step through each of the input and output worksheets. But at a very basic level, STEPL offers loading calculations by source, provides BMP efficiency calculations to reflect load reductions, and has a data server to obtain watershed data in the absence of other locally available data. In addition, STEPL also allows the user to select a suite of BMPs to apply to the watershed and modify existing BMP efficiency values if necessary. STEPL provides a tool for calculating urban stormwater BMP load reductions and a tool to calculate the combined BMP efficiency of multiple practices applied to a single drainage area. So the inputs to STEPL can range from simple to complex, but at a minimum, STEPL requires land use information and the selection of a weather station to pull in precipitation data. If applicable to the watershed of interest, animal population counts and septic system information can also be included. The type and number of BMPs must also be entered to calculate any load reductions. STEPL automatically provides default soil information and runoff curve numbers based on user-provided information, but these can be updated by the user with more specific information if desired. STEPL will also automatically subdivide the urban land use acreage into preset proportions of urban land uses, such as residential, industrial, and institutional. However, these distributions can be adjusted by the user to better reflect any actual urban land use distribution in your project area. And nutrient concentrations in runoff are also preset, but they can also be modified with more specific local data if you have it. So before we get into the demonstration, we just have a few notes on installation requirements. First of all, STEPL is only compatible with Windows 7 operating system or later, and Excel 2010 or later is preferred. And while STEPL will function on Windows 7 or Excel 2007, it does not work with the combination of the two. So if you're using Windows 7, you have to use Excel 2010 or later. STEPL also requires a significant amount of hard disk space and RAM, and as you can see those requirements here, and check those against your computer. So quickly, this is the STEPL website where the model and supporting documentation can be downloaded. Once you reach the home page, click on Model, Download, and Documentation to get to the download link. And we recommend using the 10 Watersheds template because it doesn't require installation of the program files and doesn't require administrative rights to open. We've also found this version to be more stable and compatible with a wider range of users' computer systems. For most users, this version is sufficient. It is a fully functioning version of STEPL that can accommodate up to 10 watersheds. If you need more than 10 watersheds, you can always use multiple versions of the spreadsheet and add up your total loads and load reductions at the end. As the name implies, the spreadsheet model for 10 watersheds comes pre-populated with space for up to 10 watersheds, but also room for 100 gullies and stream banks. Also included on this page is the BMP calculator, which you will need to download if you're going to be creating complex BMP scenarios. So also on the STEPL website is additional information and support, including access to various trainings, frequently asked questions. There's also our STEPL support email address that you can use to have, if you can ask any questions if you're having technical difficulties or just want to know more about the details of STEPL's functions. This is the email address. It is monitored by both Tetra Tech and EPA. So with that, I am going to turn it over to Mustafa.
Thanks, Celine.
Thank you.
So I guess we will now, the first thing we will do now is we will just do a quick, we'll look into this input data server. So we're going to start by going to the input data server to obtain some basic, learn how to obtain some basic watershed data. The input data server provides a location to obtain watershed data parsed to the county and or the watershed HUC12 level. Users are always encouraged to use local data when available. However, the input data server provides information to fill the gaps in locally available data. So let's navigate first to the STEPL website, where to access the STEPL input data server. So when you get to the website, you can navigate to the input data server for STEPL. Click on it, and then you will click on to access the input data. So you click on access the input data server for STEPL. Note that there is a warning about Adobe Flash that will come up. Click allow to proceed. Click on it, click allow to proceed. Because Flash is being decommissioned at the end of 2020, there will be changes to the input data server. EPA is working on moving the data over to a new platform to ensure future uninterrupted access. In our example, we'll do a simple example to just to see how to extract data using the input data server. So we'll use an example for a watershed, a Bull Run watershed in Northern Virginia. So when you open the input data server, you will see this dialog box wherein you can select your state. You go to the state of interest. You click on Virginia in this case, and we know that our watershed is, for example, it may be it's located in Loudoun County. Let's go to Loudoun County. We click on Loudoun County, and then can navigate down, and a list of all the HUC12s within Loudoun County are displayed. So our for example, if you would like to pick the Middle Bull Run watershed, you would just click on this. If you needed multiple HUCs, you could also press the shift button and select multiple HUCs at the same time. But for now, we just select the Middle Bull Run HUC12 watershed, and on step 4, you will click on this spreadsheet type icon on step 4, and a window will pop up. You'll notice a window will pop up with all the data with several tabs showing the watershed size, land use information, agricultural counts, we have the septic system information, and the hydrologic soil group. These are all the basic inputs that go into the STEPL model. There is also an export button which the user can click, which will export all these data into a simple Excel spreadsheet, which you can use for populating the STEPL model. So you just click on export and it will export. So the data can be used as is, or it can be used to supplement better local data. That is the most important thing I would like to emphasize. So for example, you may have a good local land use data set, but you may not have any septic information. So you can opt to use the input data server to pull in septic information to fill the missing pieces. But you can still have your own land use data in the model. So for simplicity's sake, for illustration purposes, we are going to use some nice round numbers to make data entry a bit easier, rather than directly pulling data from the input data server. Now that I have finished illustrating the input data server, let's minimize that, and okay. And we will work on a hypothetical creek called Example Creek that has been divided into 3 sub-watersheds. They are called the upper, middle, and lower Example Creek watersheds. Now, when you open the STEPL 10 watershed spreadsheet, this is what you will see. This is what you will see. You will be put. It will open up onto the input tab. This is the main page where all the watershed information will be entered. The other visible tabs include the BMPs, the total load, and the graphs sheets. For the most simple of models, these are the only worksheets that are needed. However, there are several hidden tabs that provide supporting data and fields where additional data can be added or customized. Detailed information about these hidden tabs actually can be found in the user's manual in case the user was more interested. The input worksheet is where you will select first your weather station data, add land use acreages. You can account for agricultural animals, septic systems, refine your urban land use distribution, and cropland irrigation, or customize your USLE parameters, universal soil loss equation parameters, and the hydrologic soil group information if desired. As a general note, red text fields can and should be filled in and modified by the user. The cells with black text are either fixed values or calculated by STEPL. They should not be edited. To begin, we select the state and county that are with our most appropriate weather station for our project. So let's assume that we are in Virginia, and we are located in Loudoun County. We use these pull down menus to navigate to our Loudoun County from these pull down menus. So in this case, we are going to use the Dallas Airport as our weather station, which is the closest weather station to our watershed. So we are going to assume that we are interested in treating also each of the 3 watersheds as part of a larger watershed. So there's a checkbox that determines the sediment delivery ratio that will be applied depending on whether you want to treat all the sub-watersheds as a part or a single watershed. If the watersheds are all treated individually, then the sediment delivery ratios vary by watershed. So that's the basic difference. So in our case, let's treat all the 3 sub-watersheds as a single watershed. Also, at this point, you can decide or later on, you may decide if you want to include load calculation for groundwater pollutant loads. Again, this is informational purposes only, and any BMP added to the scenario will not impact groundwater loads. The only way to adjust the groundwater loads is to manually adjust the default shallow groundwater pollutant concentrations. The appropriate location to adjust these values will be demonstrated as we move through the input sheets. So you can either check this box, or let's check it on for this exercise. So now we can move on to populating the watershed information. Each watershed can represent any size from the drainage to a single project up to a HUC scale. It is up to the user to decide on what scale STEPL is used. This can be based on both the level of detail you need in your load reductions, as well as the amount of complexity in your the suite of BMPs that you're applying or proposing to apply. So they require some thought process before you carve out your watersheds. So in our example, we have subdivided our watersheds into 3 sub-watersheds. So the first task is to let's label our watersheds in our model input worksheet. It's easiest to label all the watersheds from the beginning. So what we will do is we will call them as the first one as let's call it as lower example 3. And the second one we will call as middle example 3. And the third one, let's name it as upper example 3. And then, so what we can do is we can go back and copy for all our tables and go in, and this is a good practice too for good bookkeeping, so that you can keep track. Ultimately, you will see that this is useful in assigning the appropriate BMPs if we have many watersheds going on. Just add these in. So then now we will add the land uses in table 1. So I forgot to mention, so you will notice that as you selected the weather station, also the weather information, the precipitation information related to this weather station already got pre-populated out here in columns K and M. So let's go and paste some watershed area data. I already have them here, so I'm going to just copy them directly into table 1. It's a good idea to always space special in STEPL as much as possible as values. So as you can see, it populated the total area. And you can also see that there is a user-defined land use category. So if you do not have any specific land use, you want land use types that are from the predefined land uses, you can use the user-defined land use. It can be used to represent any type of land use, but the user needs to specify the corresponding runoff curve number and the nutrient concentrations for this particular land use type that you enter. This information must be defined by the user. In our example, we have this 25 acres of user-defined land in the lower example creek subwatershed, and then we will have to add the required pollutant and runoff information for this land use as we walk through STEPL input tables as we move through them. So in column I, for example, for table 1, also let's make one adjustment for the feedlot % paved to reflect local conditions. So in our example, we'll say that the proportion of for the lower example, we have per feedlot % paved is say 25 to 49%. So we'll make that one update and then move on to table 2, which is the input for agricultural animals, where we will add the animal counts into our spreadsheet. Column K through L, also note out here, ask about the number of months that manure is applied to cropland and pasture land. If manure is applied consistently throughout the land, you can enter a value directly. Alternatively, if there are multiple application frequencies on each land use, you can use the manure application button to calculate the number of months across each land use. This is the manure application button out here at the top of table 1 in the right hand corner. Let's just now paste the agricultural animals that we have. Counts. So we have counts out here for animal for each of these. Then we can go and paste specially here as values. Now let's let's look at the manure application. So let's assume that in our example, there is no manure is applied to cropland pasture in the lower watershed. However, in the middle example creek, we will assume that manure is applied to all the cropland for 2 months out of the year consistently across the acres. We will assume the manure is applied 1 month per year for pasture land. So let's enter a 2 in cell K3, 33, sorry. And 1 in out here for pasture. For the upper example creek, there are, let's assume that there are, if we had, for instance, multiple manure application frequencies. So we will use the manure calculator for these purposes. And we click on the manure application button. This opens up the manure calculation worksheet. This will provide the values for columns K through L in table 2, which we'll look at, where we will start with, let's say, cropland, for example. We know that cropland has a total acreage of 12,750 acres. So let's enter the 12,750 acres out here in the cell B2. Then we enter the acreages with different manure application frequencies. The total acres in the calculator needs to equal the total cropland. So let's again paste let's get some manure application frequencies here. See. Let's put these are applied as different treatments in the watershed. So you can paste them here, and you can see. Let's go down. So in our example, as you can see, manure is applied 2 times a year to 3,000 acres, 5 times a year to 1,000 acres, and 4 times a year for 7,000 acres. The remaining acres do not receive manure. However, as you still need to include these remaining 1,750 acres here in the calculator at 0 months of manure applied. Once these acres equal the total acres of cropland cell B27, where it does a quick check of the total area, that the total area matches the total area that we entered in cell B2. That's a good way to ensure that the areas are checked. And we take the value from C25, which is we got a value of number of months manure applied as 3. So we take that and we enter it back. We go to our input sheet and we can enter it out here as a number of months for cropland. Similarly, this can be done for pasture land if various different treatment agent application information is available. While we won't do it again during this demonstration, you can just use the calculator if you would like to do that in the future. We just override the previous calculations and just do the calculation out here as many times as you need to fill out the manure across all the watersheds. Let's move on to table 3, which is the septic systems and direct discharge data in table 3. The input worksheet comes pre-populated with the national average population per septic system and the average failure rate. Ideally, these should be replaced with locally specific values. We have more specific data for our watersheds in this example, so let's add it out here in addition to the number of septic systems that we have or information that we have in each watershed. If there are known, let's first do that. Let's go back to our spreadsheet and we will paste in our let's go here, number of systems, population, paste this as values. and we have our own septic failure rates that we have calculated. If there are known, the other two columns are for direct discharges, and if there are known direct discharges, they can be added here too. This table also includes an input for any practices to reduce direct discharges. As a percentage you can be applied. So this is one of the few places where load reductions are applied on the inputs worksheet rather than the BMP's worksheet. We will assume that there are, for example, there are 2 direct discharges in the upper watershed. If one for a family of 4 and another for a 6-person household, for example. So these two systems are serving a total of 10 people. So the number of people in the upper watershed, we will enter the 2 households, 6 plus 4, 10, the number of people. And if the implementation actions in the watershed, say for example, result in installation of a sewer system for the 4-person household, then we can eliminate the direct discharge, and we estimate a percent reduction of say 40% based on that. We can enter 40 out here. And note that these values are expressed as the number of people, as I mentioned before, by the direct discharge, not the number of discharging systems. Table 4 is a hidden table. It provides default values for the universal soil loss equation. Let's unhide it here quickly. You can see it. This provides some default information. The universal soil loss equation is used to calculate annual sediment load, with all the different parameters that go into the universal soil loss equation. These are pre-populated based on county, and it uses sediment delivery ratio to calculate the delivered load. These parameters can be changed if more specific information about the watershed is known, or these are externally calculated or more refined using the RUSLE2 tool outside STEPL. In this case, we do not have any special information, so we will use the default values. Next, let's go to table 5, which has the soils data. The input data server provides us with the soils for our watersheds. So we will, let's change and we know that all our watersheds have a C soil. I mean, again, if the user calculates it externally, they can do that. As you click on this radio button, you can notice that the SHG selected also changed to C. And in addition to this, for each of these watersheds, you also have the soil nutrient concentrations from column H through J. This can be customized again if more better values are available than the defaults that are provided out here in table 5. Table 6 through 7a provides default curve number and nutrient concentration information. The user can adjust these as needed if there is more locally relevant data again. And since we have included a user-defined land use, we need to make sure to update tables 6, 7, and 7a with specific information for that particular land use that has been defined. So if you do not have a good estimate of the runoff curve number and pollutant concentrations, we recommend you do not use the user-defined land use. We just roll that land use into whichever existing category best fits it. These are default values provided in table 6, but they are just placeholders and should be updated to reflect the curve number for the user-defined land use. Similarly, for the nutrient concentrations in the user-defined land use must be added, otherwise the pollutant load from the land use category will be 0, as the values currently are set to be 0. So in our example, we will assume our user-defined land use has a curve number of 65. Since our watershed has all C soils, we only need to update that for the urban the category out here to 65. that we just did here. We also need to provide values for tables 7 and 7a. So we will assume, let's say for table 7, we will assume nitrogen concentrations of 3.8, phosphorus of 0.2, and BOD of 7.5. And we will notice that the E. coli concentrations are left blank for all land uses. Please note that this is just a placeholder field and was built into STEPL, but EPA has not developed any default values for this pollutant at this point of time. In addition, we also need to update table 7a with the shallow groundwater concentrations, which we let's take it as 1.7. We will enter, and phosphorus is 0.04. And we are all done with these tables. Let's go to table 8. Table 8 breaks out the urban land use categories into different categories. Like there are into 9 distinct urban land use categories. The total urban area is automatically populated from table 1. As you can see here, the total area. A default urban distribution is provided. And this is just an initial distribution, and it can be and should be again changed by the user, since it's unlikely that these default values are correct for a given watershed. It should be adjusted according to the best available data. So in our model, the lower example watershed is like, for example, we note that the lower example watershed is 25% commercial. So let's change this to 25 in terms of the distribution, and the industrial is 20, for example, and the single family percentage is 10%. Note that the total area has to add up to be 100 out here. You will notice now it's 100. So now that we have reflected our land use distribution, let's look at table 9, which provides an opportunity to enter information about the irrigation on cropland. The total cropland area are automatically populated in table 1, as you can see out here. If you want STEPL to account for loading for irrigation, be sure to include the average irrigation depth and frequency across each watershed. To represent existing conditions, the water depth before and after BMP should be the same. To represent the reductions from irrigation management, for example, the water depth after BMP should be adjusted. So in our scenario, we will assume that all 1,700 acres of cropland, let's say, are in the lower example creek watershed are irrigated, and the farmer is using 2 inches of water per irrigated week between May and August, let's say, for example, and then they've determined that they could reduce water use by say 25%, which amounts to like 1.5 inches. So let's the water depth is 2 inches. And the reduced water depth after irrigation is 7.5 inches after BM this. And there are since there's about 16 weeks from May through August, we will put 16 number of times this is applied, is 16 in the irrigation frequency field. The same process should be followed for other watersheds if needed, and if applicable. Table 10 has default values for pasture and nutrient concentrations, which do not need to be edited. For this example, the default values in table 10 are the average EMCs taken from previous versions of STEPL. Hence, all 6 categories of low, medium, high, with and without manure are the same. This table has been expanded to allow for the user to apply for manure application. The EMC values for all the 6 categories need to be updated based on the published literature and after review and approval from by EPA. These can be updated by the user if better numbers are, of course, available based on local data. To finish with the inputs, there are a couple of key factors we need to point out. Land use distribution is critical to the results, and you will get from STEPL. So make sure you use the most accurate data you can find. And as a reminder, users should modify the inputs with any local data you have that is more accurate than the default value. So also the user needs to be sure to focus the data collection resources on sources being addressed for their project. If you're using STEPL for load reduction calculations, for example, and then you're working on an urban watershed and implementing urban stormwater management, the agriculture information will not affect your load reductions, just the loads in the watershed. So the total amount of data you need to collect will depend on your objectives. We will pause here for a few questions on inputs. This is a good stopping point before we move on to the BMP step.
Sure. Hi, this is Don Way from EPA headquarters, National Non-Point Source Program, and I'll be moderating the Q&A portion. Amanda asks, when would you not want to treat all watersheds as a single watershed, and can you give an example or two?
Yes, if you are interested in knowing or understanding what is the impact due to only a specific watershed, then you may want to just uncheck that, and so it will just use it will compute as watershed specific sediment delivery ratio. So you will basically the sediment delivery ratio is calculated based on the drainage area. So it will calculate a delivery ratio based on your drainage area. So you can get more refined estimates just for that particular watershed. So by treating the watershed as when you say, let's go off, when you're saying you treat all the sub-watersheds as a single watershed, so when you're combining, for example, all these 3 watersheds, you're increasing the overall total area, and the sediment delivery, the greater the drainage area, the smaller the sediment delivery ratio, because there is more trapping in the watershed. So I don't know, hopefully that answers your question.
Don, are you muted? Are you trying to ask us another question?
Sorry about that. Yes, Andrea would like to know how much watershed data does STEPL have for users versus what data might the user need to supply for themselves? And how do they know whether to use the default data or user supplied data?
The one thing to understand is the STEPL input data server provides data at the HUC12 level. If you have a more localized or smaller watershed, you will need to do your own land use analysis to come up with your watershed or site scale.
So I'll add to that. The input data server provides the basic HUC12 information of land use, the agricultural animals, the septic system information, and your soils. I don't think I'm missing anything. That's about it. That's what it provides.
Right, and I'll just add that if you have more up-to-date specific information about your watershed, you can easily override that data. Correct? We'll take one last question, and that one, we received a few on the different land use types available. And if you would like to model a land use that you don't see, what are the options for user-defined land uses? Do we just get one? If you want to model, say, a golf course, for example.
Yeah, well, yes, you only get one. If you have multiple, what you can do is you can either make multiple copies of your spreadsheet and use the user-defined, or with a little bit more care, you can use, it's more for an expert user, I guess, but you can use the other slots for the other land uses, but it would require a lot of, you need to be more careful. I guess you can use the forested slot if you want to. But I would, yeah. Well, the simple answer is only one user-defined land use for STEPL. Or if you want to use multiple other categories, you may want to make copies of this spreadsheet and do it. Because it's all in an aggregate, you can just add up the loads in the end and summarize them.
Okay. Well, so I said that was the last one, but Gregory asked a great question that maybe we can get addressed real quickly. He wants to know if you infiltrate nitrate using a BMP, would STEPL then calculate a groundwater load? How is the nitrate input accounted for, its state and transport?
The way STEPL does, the way STEPL calculates groundwater is very simplistically. So STEPL calculates groundwater as a fraction of the precipitation rate. And these fractions are determined based on the hydrologic soil group, and that fraction that is infiltrated, that is calculated, a volume is calculated, a runoff volume is infiltrated, volume is calculated, and that volume is multiplied by the specified shallow groundwater concentrations that are specified out here in table 7A to calculate a loading. So you have specified nitrogen phosphorus loading concentrations, which are ultimately used by multiplying with the volume, shallow groundwater infiltrated volume. More details on the equation and the specifics, if you are more interested, you can find that in the user's manual.
Great. Gregory asked a simple question, and it was a very simple, straightforward answer, Mustafa. No, it was a great question, and there's a lot to it. So, but we have over 450 people tuned in right about now, and a lot of material to get covered. So there's a lot of questions that we're not going to be able to get to. We apologize for that. We will be doing follow-up after this webinar, and we're going to go ahead and move into the next phase now.
Thanks, John.
Mustafa, are we ready for the next part of the webinar?
Thank you. I was on mute. Apologize about that. So the main interface for non-urban BMPs is the BMPs tab. Just click on the BMPs tab, as you can see here. In tables 1 through 5, general BMPs can be added for cropland, pasture, forest, and the user-defined land use and feedlots. And there are also buttons at the top to access the urban BMPs. There's a gully and stream banks erosion, a button to, this is actually a button to calculate combined BMP efficiencies. And there's also a run button for a solver option, which I will discuss a little bit later. So you can see the tables. Let me just please scroll down a little bit. same. Okay, so as a start, before we just illustrate the non-urban BMP application, let's quickly, I would like to quickly illustrate the gully and stream bank erosion worksheet, which can be accessed by clicking on the gully and stream bank erosion button at the top of the BMP worksheet here, as you can see. So when you click on that, it will open up another worksheet. The worksheet calculates both the initial loadings from gullies, stream banks, and also reductions from stabilization and restoration BMPs. Gully loads are based on annual erosion rates, which are determined by the volume of gully and volume of the gully and like the soil weight times the soil nutrient concentration. Stream calculations are similar, except that they include a lateral recession rate as well. Hence, you'll notice that the watersheds here, unfortunately, are labeled 1 through 10 rather than providing a space for our own naming convention. So we need to make sure that you are applying the gully to the correct watershed. We will assume that there are 2 gullies in this project area and fill in the dimensions for each. Assign each of the gullies to the correct watersheds by clicking the up and down arrows and then click on the radio button. So these are the up and down arrows that need to be clicked and then click on the radio button. So for the gully number gully 1, we will have an application in watershed 1, which is the Lower Example Creek watershed, and it is 4 feet wide at the top, and next example, and it's 1 foot at the bottom and 1 foot deep, and it runs, say, for 50 feet long, and it started, say, 5 years ago. And according to our data, it's a sandy loam. So when you go and you click, this is the up and down button which I was talking about. You will go down and you click on sandy loam. It's a sandy loam, and when you click on the radio button, as you can see, the soil dry with the other parameters also update. Selecting the correct soil is important because it affects the nutrient correction factor and does the loading. And the correction factor is, as you can assume, is related to the type of soil, and there is these are captured by a table that can be shown at the right of this. You can probably look at it later on. Based on each soil type, the soil information is provided out there. In the Upper Example Creek watershed, which is dubbed watershed 3, we have a gully number 2. So let's click on watershed 3 and select it here. It's going to be applied to gully number 2, which is let's say a 10 feet on the top. It's 2 feet at the bottom, and say it's 4 feet deep, and it's 230 feet long, and say it took 15 years. 15 years to form. And we will change the soils to, again, to be fine sandy loam in this case. Fine sandy loam, you click on it. And the BMP efficiency value also, if you can notice out here, is where you will enter either 0 if the gully is not to be fixed, or some efficiency value related to BMP that is used to address the gully erosion. The default efficiency value is set at 0.95, but the user should include more project-specific information if it's available. We will assume that the gully 2 is fixed through drainage management and restoration, and we will apply the default efficiency value. Let's keep it at 0.95. For gully number 1 in watershed 1, which is the Lower Example Creek, it is a smaller gully, and there are no plans to fix it. So let's assume that the BMP efficiency, there are no plans to fix it. So BMP efficiency would be set to be 0. As you make changes to the BMP efficiency values, as you will see, the Load reductions also are calculated on the fly based on the formulas. And for the, let's go to the impaired stream banks now. We are only concerned with the length that is impaired. So you don't really need to enter information for all stream segments in the watershed, just for those in the concern. Each side of the stream is calculated separately to allow for different conditions on each bank. So we will assume that there is an impaired stream reach in lower Example Creek, which is watershed 1, and one in middle Example Creek, which is watershed 2. We click on the arrows to assign banks 1 and 2 for watershed 1, and banks 3 and 4 for watershed 2. So banks 3 and 4 are associated with watershed 2. Let's do watershed 2 and watershed 2 in out here, and then you click on this radio button. So we have assigned the correct banks to the correct watershed. So for bank 1, for example, we have say a 1,500 feet long, and it is 8 feet high, and it has it's a severe lateral recession is seen out here. We click on severe. Bank 2 is 1,200 feet long, and it's 6 feet high, and we say this one is kind of like a moderate lead recession, and both are sandy loam, having a soil sandy loam. Let's click on sandy loam here. As you can see, the load reductions are calculated on the fly. So again out here. And watershed 2, what we have, say 2 of these are 500 here, and then both are 4 feet, 4 feet, 4 feet, and both have moderate lateral recession, and both are sandy clay loam, for example. Anyway, I will just leave this at say clay loam. It doesn't matter. For our example, we will assume that stream restoration has been undertaken on both the streams. So we'll assume that the restoration reduces 90% loading. So let's change this BMP efficiency to 0.9, and here's 0.9. 0.9 here. And you can see that now that we are, the load reductions are calculated on the fly. Now that we are done with gullies and stream restoration, we can click on the close worksheet, which is located at the top of the worksheet, and just return to the, or we can just return to the BMP tab. So there is, you can click on this close, and close it. And once you return to the BMP tab, you can see again the BMP worksheet comes back, and it provides a separate table for each land use where the BMPs can be entered for each watershed. And it's most basic. You can select BMPs and the percent of land use on which it is applied. The efficiency values will be calculated automatically. Alternatively, you can create a combined BMP efficiency to account for multiple BMPs on non-overlapping areas of the watershed, or use the BMP calculator to deal with BMPs in series and parallel. We'll start with this example and work on to a more complex BMP scenarios. The first step is to update the watershed names in the watershed for the inputs tab. I will just quickly just update for the top one, just so that we have it for illustration purposes. Just update it for all of them. Okay, I think that we'll just keep this the way it is. to save some time. Let's assign a single BMP per land use per watershed. Let's see how we do that. So adding a single BMP means only one type of BMP is on a given land use. There may be several instances of that BMP, but there is only one type. So for example, if we have contour farming, which is the only BMP in the lower example creek watershed, we will add all the acres of contour farming throughout all the cropland. So if there are 250 acres now, we add up all the contour farming areas and then we calculate total acreage of contour farming to be 250 acres. The input that is required is the percent area BMP applied. So we need to calculate that, and that will be the 250 acres of contour farming divided by the total cropland acres, that is 1,700 in this case, which is the area of the cropland in the lower example watershed. If there are so 250 divided by 1,700 makes gives you about 14.7. We enter 14.7 out here. The BMP efficiencies in and also we know that this is contour farming. So let's navigate to contour farming. And once you click, you will see that the efficiencies are updated out here. So once you are done this, you can apply the same process to any of the land use types. This, even I've done it just for cropland. We can, if we know if there's only one specific BMP, it can be applied in this manner. Now there is also a BMP optimization feature on this BMP worksheet in this 10 watershed STEPL template that is not available in the regular STEPL installation package. This feature allows the user to this is what I'm talking about. This feature allows the user to identify a target load reduction in a suite of BMPs, and then you set the upper and lower bounds on each of the BMPs to indicate the acceptable range of acres of implementation for each practice. From there, the solver will identify a level of implementation that will meet the target loads. This tool will only work for non-urban BMPs, and the optimizer, it's very important to note, the optimizer is intended to maximize the load reductions and minimize the treated land use area needed based on the suite of BMPs selected by the user. So let's do an example. For example, if the target load is say 15,000 pounds, that you want to target a reduction of 15,000 pounds for nitrogen. So you will first go here into cell M, and you will, once you click on that cell, you will see this pull down menu. You can select your pollutant of concern. Here it's nitrogen, so you already have that selected. And here we enter your target load reduction, which is 15,000. We want to reduce, you want to have a reduction of 15,000 pounds. And we will now apply our minimum and maximum area constraints. So for watershed 1, say for example, we have a forested buffer. See, this is a forested buffer, and then for watershed 2, if we have conservation tillage, let's put in all our BMPs that we were wanting to implement, and we have contour farming. And say we also are having some pasture land BMPs, which are say we have in watershed 1, we have some livestock exclusion. Exclusion fencing, and then we have some heavy use area protection. And we have a critical area planting in the third one. So once you have identified these, you can add your constraints in the sense for watershed 1, this BMP has a minimum constraint that you can apply from 0 to 40. And the next one, you have a constraint, you can apply up to 70% of the watershed of the land use. And then you 10, and then these are 100. And you have 100 here. And this is critical area planting is only 10% allowed. 10%. So after entering the BMPs and constraints, we click on the solver button. This is the solver run button. So you will notice that this BMP percent, this will suggest a percent area BMP applied suggestion. Once you said okay, you will see this will be updated. So we can see when it finished, you can found a solution. If the solution is not found, sometimes it's possible that it cannot find a feasible solution, optimized solution to meet the required constraints, and the pop-up will notify you that a solution was not found. Now you can see that it's important to remember the optimizer does not account for costs or other factors. It is to provide a general guide. It may not always yield the most feasible results based on implementation, but can provide an initial guide to the level of implementation that could be needed to meet the load reduction goal. The user should use best judgment when determining how to rely on the results of the solver for planning purposes. For example, as you saw in our scenario, the solver found a solution that only used cropland BMPs to meet the load reduction goal of 15,000. If you can see here, this is what it found. In reality, there may be more types of BMPs that could be used to achieve a different percent of level of implementation. As you can see here, none of the pasture land uses were used. Again, we will let's take a brief pause out here for questions on basic BMP inputs, gullies and stream banks, and on the run solver option.
Okay, sure. So we had somebody ask about if there is some sort of a guide on what's considered low, medium, and high gully erosion rates. Mustafa, you might be on mute.
Sorry, yeah. I do not know of any guide. I guess you would have to have your local stream restoration expert weigh in on that, or a field person out there. Aileen, do you have any thoughts on that?
There is a narrative description here of stream erosion, but as far as the gullies, I don't think we have any specific data on that.
It's kind of more qualitative, yeah.
Yes, yeah. So there's some qualitative descriptions for the streams here, but not for the gullies, no.
Okay. All right. There are some questions about BMP use. Is it possible to analyze more than one type of BMP per watershed? I think we're going to get to that, but short answer for now.
Yes, we're about to talk about that.
Okay, yeah. And then also, I guess maybe foreshadowing, want to know about, how you specify the areas that each BMP are applied to. I think we're going to get to that as well, correct?
That's
well,
correct, yes.
We'll specify an acreage, yes, if that's what that question means.
Sure. Yep. Okay. All right. So I think we're ready to move on.
All right. Okay, so those were some good lead-in questions. So what I want to do, bear with me because we have to show you multiple things at once here. So we're going to quickly pop back to our PowerPoint. Okay. And so we just talked about how to represent one BMP on one land use, but now we're going to talk about BMPs in parallel and series configurations. This gets to multiple BMPs on the same land use. So I want to illustrate these different ways to represent BMPs. So it's important to know how the BMPs are placed in the watershed because the aggregate efficiency is going to be different depending on their placement. So we have parallel BMPs and series BMPs. We can also have combinations. So parallel BMPs are BMPs that treat separate areas, but both areas eventually drain to the same water body. That's our left example here. And so this example shows two treatment areas, one with cover crops and one with conservation tillage. These are in a parallel configuration. They're both in the same watershed, but they treat distinct and separate areas within the watershed. On the right, we have series BMPs. This is more than one BMP treating the same area or a portion of the same area. So in this example, we have cropland with conservation tillage, and it also has a grass buffer. So the same runoff is basically flowing through two separate BMPs before reaching the water body. So this can also be thought of as a treatment train. And we can also have combinations where you have parallel and series BMPs in the same watershed, where one portion of the watershed is treated by multiple BMPs and another portion is treated by one or more other different BMPs. So in our example on the bottom here, this combination, we have conservation tillage cropland also treated by a grass buffer, which then flows to a settling basin. And then in another part of the watershed, we have cover cropland that is then eventually also flowing to that same settling basin. So now we're going to switch back to our model here. Okay, so if you're using more than one BMP on crop or pasture land in a given watershed, and the BMPs are in a parallel configuration, you can use the combined BMP efficiency tool to create a combined BMP efficiency that you can then add to this worksheet. To do this, we're going to click on the Calculate Combined BMP Efficiency up here, and it's going to open up this tab for you. So this tool accounts for multiple BMPs on different treatment areas throughout a single watershed. And it assumes that all practices are in parallel, so there's no overlapping treatment areas in this scenario. If you have BMPs that are in series, you're going to have to use the BMP calculator, which we will discuss in a minute. So once you're on this sheet, you enter the total land use for the type of land you're working with, and then select your land use. So you have your choice of cropland or pasture land from the drop-down menu, and then click Update BMP List to update the BMPs that will be available in this section here.
Hey, Aileen, I'm going to break in here. There's been a few people who are wondering if it's possible to increase the magnification of the view because there's some severe collective eye strain. Excellent.
Getting better? Okay.
Yeah.
All right. Sorry. It's really big on my screen.
We
Hard to know what other people can see. All right. So once we're here, we're going to enter the total land use for our land use. And we're going to work in Middle Example Creek. So there are 2,550 acres. And we're going to work with cropland. So we want to make sure we've selected cropland from our choices. And then we click Update the BMP List. And now we have to add each of our BMPs. So these are BMPs treating totally separate portions of this watershed. So let's say we have 50 acres treated by a bioreactor. And we have 400 acres of conservation tillage. And 700 acres of nutrient management. and 100 acres of two-stage ditch. So at this point, we've applied BMPs to 1,250 acres out of our total 2,550. But we need to make sure that these totals match. So we need to add 1,300 acres of no BMP. And you'll see that this corrects to say OK. So from here, we have in row 25 the combined BMP efficiency for this suite of BMPs. So we want to copy this and come back over to the BMP tab. And we want to remember, so we're going to come down here to table 7. So we were working in the cropland for watershed 2. So we want to paste our efficiency values here in the combined efficiencies table. You want to make sure you paste the values, not the formulas, in order to get the numbers here, otherwise it'll mess it up. So then we're going to go back up to table 2. And we're working in the middle watershed. So we're going to pick from the drop-down list, combined BMPs calculated. This will pull from table 7. And since we accounted for 100% of our cropland area, we're going to put in the area BMP applied is 100%. And you'll see that updates the efficiencies to the full efficiency value. So you can use this combined BMP efficiency calculator for as many BMP combinations as you need. You just overwrite the data each time and copy and paste the results from row 25 into the correct location, correct watershed and land use in table 7 on the BMP worksheet. If you want to save a copy of this, so you have a record of what BMPs went into your combined BMP efficiency, just click copy to log. And it takes a second to run. But it will create a Word file for you that has this log for you, so you'll have a record of it. And be sure to click this before you overwrite it, or you'll lose your information. It'll be overwritten by the next set of data. All right, so to represent more complex configurations of BMPs, we're going to talk about the BMP calculator. So let me close out of this. All right. The BMP calculator can be accessed from the add-ins menu, which is up here at the top, add-ins, and you'll have a stepple option. And then you pick BMP calculator, and it'll open up for you. And if this is the first time that you're accessing the calculator, it's going to ask you to identify the file to run. So you need to navigate to where you saved your stepple files, which oftentimes is just in the C drive in a folder called stepple. And click on it's a file called bmpcalculator.exe, then click open, and it will open up this calculator as you can see here. It didn't do it for me because I've opened this many times before. So now we're going to walk through some examples using some illustrated watersheds. So bear with me while we look at multiple things at once. Okay, so here's an example of parallel BMPs only. Since this is cropland, you could also have done this exact same scenario over in the combined BMP efficiency calculator, but we're going to work through it here to show you how you could do it in either way. This is one of the simplest examples, so it's easiest to start with a simple one. So we're going to work in Middle Example Creek again, and we're going to say that this watershed has 3 BMPs, a forest riparian buffer, a contour farming, and cover crops. And so each of these practices, as illustrated, is treating a separate area of the watershed. So the BMP calculator provides boxes in which to build out your BMP configurations. So we're going to set up a box for each BMP by clicking the icon at the top, which is half white and half blue. I don't know how else to describe it, but if you hover over it, it says add a new BMP. So we're going to add a new box for each of our BMPs. We have 3, so we need 3 boxes. So then we double click on each box to open up the input fields and populate them with our watershed information. So there's a BMP list where you want to make sure you pick the BMP from your correct land use. So we're going to pick, we have forested riparian buffer on 25 acres. And you'll see the efficiencies appear here. And then you click OK. Then the next one, we have 250 acres of contour farming. And then we click OK. And then the next one is 300 acres of cover crops. And we click OK. So now we have our 3 BMPs out here. And then we add another box to show that each of these BMPs is routing into the same watershed. So we'll add another box, and I like to just move them around so you can visually show them in the order that you might think of it in your mind. So this box represents the total watershed. So if you have any additional cropland without any BMPs, you can add that acreage here, but leave the BMP blank. So in our example, we have a total of 575 acres addressed by BMPs, but then we have 1,975 acres which we have not applied BMPs to. So we're going to open up the box for our watershed and add 1,975 acres and no BMP to represent the fact that there's no treatment. So if your BMPs did happen to account for 100% of your acreage, you wouldn't need to add any acreage. This would just be a blank box that represents the watershed. So now we need to connect all of our BMPs to the watershed. So with your mouse, just left click on each BMP box and drag a line down to your watershed box, and they'll automatically snap to it. And if you make a mistake and you've drawn a line to the wrong box or in the wrong direction from one box to another, just click on it and it turns red, and you can delete it and draw your line again. Same thing for the boxes. Click on them and you hit the delete key and it'll go away. You can also use the little scissor icon up here to delete a box. So once the watershed is configured the way you like it, we're going to click on the Calculate Combined Coefficients button at the top. It's this box with dots in it and 2 down arrows. And then as you can see, our total acreage check is here. So 2,550 is our total cropland acreage. And then here's the combined efficiencies for all of our cropland acres in this watershed. Anytime you edit your scenario, make sure you hit this calculate the combined BMP efficiency icon again, so it'll recalculate and update, but it won't do it manually. You have to click the button. So once we have our output, we can copy these values over into table 7 on our BMP worksheet. So let's move this over here. And we're in the cropland for watershed 2 again. So shrink that down. And then we just enter our B efficiencies. So we have 0.033, 0.044, and 0.039 combined BMP efficiencies. And then we can scroll up and the BMP efficiencies have been updated. And we can leave this at 100% because you've treated 100% of the watershed with the way you've configured your combined BMP. So if you want to save this scenario so you have a record of it, just click Save, and you can name it whatever you want, and you'll be able to reload it by opening a file later. And you'll you'll be able to take a look at your scenario in the future. Just remember, whenever you do that, when you reload your scenario, you need to click the calculate combined efficiency again, so it will give you the values. Otherwise, it has a tendency to give you an area of 1 acre, which we know isn't right. So just make sure you recalculate it every time you use the scenario. So the next example we're going to work through is BMPs in series. So we'll get a new BMP calculator. And here's our simple BMPs in series example. So now we're going to work in pasture land in Middle Example Creek, and we have 525 acres of pasture in this watershed. So these acres are treated by 2 BMPs, livestock fencing and a forest riparian buffer. And these practices are arranged in a way that the runoff from the fenced pasture land also travels through this buffer. So we're going to start out the same way by creating boxes. We have 2 BMPs, so we create 2 boxes. And the livestock fencing is the upstreammost BMP. You can do it in any order, but I just find it works best for me to work upstream to downstream just to keep everything kind of mentally straight. So we're in pasture land now, so we need to scroll down to the pasture BMPs. And we find our livestock exclusion fencing. And we put in 525 acres. So now we're going to add the forest buffer. Again, make sure you pick the pasture land forest buffer, not the one from cropland. And now we're not going to add any acreage because this BMP is also treating the same 525 acres as our fencing is. So we just leave the acreage as 0. Click OK. And now we're going to connect a line between these two to indicate that the same acreage is being treated by both BMPs. So we draw a line from our livestock fencing over to our forest buffer. And then we click calculate. And there's our result. So 525 acres and a combined BMP efficiency that's higher than either of the practices individually. So the same thing would apply. We would come back over to table 7 with this value, and we're in pasture land, so we want to go to the pasture land column or row, and we would just enter our efficiencies here.
Aileen, make it bigger. Some of us can't see.
The spreadsheet or the calculator?
Just
Spreadsheet?
whatever screen that you happen to be highlighting.
Okay.
And just be aware that there are those of us like myself who suffer from severe eye strain.
Okay.
Thank you for being kind.
All right, so there we have our combined efficiency. And we come up to pasture land and we're in the middle watershed. So we'll go back and pick BMPs, combined BMPs calculated. And again, we're at 100% of the acreage, so we put 100 in the percent area applied. And that's your updated efficiency. So now we're going to walk through an example of parallel and series BMPs. We're going to assume, let me rearrange things here. And if the BMP calculator is small, I don't think there's any zoom features on this. There's nothing I can do about that, so I apologize, but I'll try to keep the spreadsheet bigger. So in this example, we'll start with a new calculator. We have 975 acres of pasture to work with. And we're going to assume that we have a similar configuration of livestock fencing and buffer down in the lower part here. And then in addition, we also have 100 acres of forage planting further upstream and 25 acres of riparian buffer on the other side of the stream. So if you add all of this up, it amounts to 875 acres. So we'll have to add another 100 untreated acres in this scenario as well. So let's start with our BMPs. We'll add one for fencing and one for the buffer, and we can go ahead and do this one the same way we did before, where we pick fencing on 750 acres. And forest buffer on 0 acres. And we'll go ahead and connect those two right now. Then we can add our other BMPs. We have forage planting. On 100 acres. And we have buffer on 25 acres. And as I said, we also have 100 acres of untreated area. So we don't want a BMP, but we'll add 100 acres. Now we want to create another watershed to represent, or another box to represent the entire watershed so we can tie all our practices together. So we're going to tie our series practices to the watershed, and then our parallel practices, and then our 100 acres that don't have any additional BMPs. And then we'll click run. And there's our 975 acres and our combined efficiencies. So this is entered in, I won't do it again, but we'll enter it in table 7, and then you pull it up in the appropriate section of table 2 as a combined BMP. I have one more example that's a little more complex. I think to save time, because we're running a little behind here, I'm just going to pull it up. I'll demonstrate what it looks like as an example. So this is a more complex one where we have 3 sub-drainages, one without any BMPs, one with 1 BMP, and then a couple series in parallel in another segment of the BMP. So what this looks like, I have a saved scenario. So I open it up and I find my saved BMP calculator scenario. And this is what it looks like. And here you can see an illustration of if you don't recalculate when you open it, it'll just show you 1 acre and no efficiency. So we're going to click calculate. And here's the total acreage that we have for this scenario and the efficiencies. Now in this scenario, this is the upper example creek, and we know that there are 12,750 acres of cropland in that watershed, but our BMP scenario only represents 4,650 acres of cropland. So we did not build a scenario that represents 100% of the cropland in that watershed. So what we can do to account for this is we want to make sure we enter our efficiencies in table 7. This is watershed 3 cropland, so we'll enter these here. And then we'll go up to cropland in watershed 3 and pick our combined BMP is calculated. And then when it comes time to decide for the area of the BMP applied, all we have to do is say 4,650 acres divided by the total 12,750 acres is about 36.47%. So our BMP applies to 36.47% of the cropland in the upper watershed. And you'll see that adjusts the efficiencies accordingly. So we've done these examples with pasture and cropland, but the BMP calculator tool can be used with any land use that's in STEPL. That includes the forest and the urban. We'll go through an urban one in a little bit, but with that, let's just take a quick pause here and see if there are any questions about the calculator or combined or series BMPs.
Yeah, so Charles wants to know if you can add a large set of BMPs essentially as a single BMP if you've derived reduction efficiencies, and then basically add them as a batch instead of one by one. Can you talk about like whether the wisdom of this idea, what sort of factors should be considered if considering this type of approach?
So I think what that question is asking is if you already have an efficiency, a suite of an efficiency for a suite of BMPs that you're going to be using, you don't need to use these combined calculator efficiencies or the BMP calculator. You can go directly down to table 7 and enter your efficiencies here. Obviously, that relies on your efficiencies, not the default value efficiencies in STEPL. So you have to be confident in your efficiency values to do that. But there's no reason that you can't come directly here and enter a combined efficiency from something that you've calculated externally from STEPL.
Okay.
Does that address the question?
It did for me, hopefully to Charles too.
Okay.
Yeah, so can you remind us, can you show us how we get to the BMP efficiency tool?
The calculator?
Yeah, the calculator.
Yes. So maybe if this, I don't know, that I can't zoom in on the menus, unfortunately, but you go to add-ins at the top here. I know it's a little laggy, so I'll wait and make sure. And then over on the left, there should be a drop down for STEPL. So you click that. And then you go to BMP calculator. Right here. And click it.
To make a point on that, Aileen, you see, I think the BMP calculator from the add-ins for a menu can only be accessed if you have completed the standard STEPL install. Now, since if you're just picking up this spreadsheet as a standalone, then you would need to go to the EPA's STEPL website and just download the BMP calculator. It's called STEPL 4.4 BMP calculator. It's a zip file. You can just download it, and there's also a user's manual along. So it works standalone. So you can just click on the executable, and it will open up the same thing, the interface which Aileen was showing. In case you have not done the standard install, yeah.
All right, yeah.
You can navigate to it in your file folder just as easily, yes.
Gotcha. All right, so that's it in terms of the cues from the folks. A lot of folks have stated that they thought the webinar was going to be for an hour and a half, and now we're into overtime for that. We're wrapping up in 17 minutes, is that correct?
That is the goal, yes.
Okay. All right, so for those of you who have waited this long, bear with us. We are approaching the finish line. And thank you.
Okay, so we're going to move on to the Urban BMP tool, which you can get to from the BMPs tab. It's just the button at the top left. So when you first open it up, this pop-up will come up. You can close it for the time being, and one of the first things that you should probably do just for housekeeping is put your watershed names in. I'm only going to do it in one just to save time, but put your watershed names in to keep things straight, because whichever watershed you're applying to needs to be consistent with your acreages from the inputs tab. So one of the things to remember here is that there's a default land use distribution already provided. If you wanted to change it back on the inputs sheet, that's where you should do it because it will pull in all of those acreages into this tab. So I also wanted to point out that there are in table 1 default values for the EMCs for urban land use up here. These can be modified if you have any locally relevant data that you think is better than the default values. Feel free to change these. So we're going to reopen with this Urban BMP tool button, the pop-up that initially came up when we opened this tab. We're going to start with a simple single BMP on a single land use. So in the same way that with the non-urban BMPs, you can have more than one instance of a type of BMP on land, but you want to do an aggregate drainage area for all of that type of practice in any one land use. So let's say that we have in watershed 1, you want to pick it from this, watershed 1, on the commercial land use, we've got 12 bioretention systems. We want to add up the drainage for all those systems and apply that to this table. So we want to pick bioretention and we say, okay, the 12 systems add up to 42 acres of drainage treated. So we'll change this to 42 and we'll click apply BMP. And you'll get confirmation that it was applied. Click OK. And you'll see in table 2, 42 acres of commercial land have been treated by a BMP. In table 3, it'll show you that it was a bioretention.
Aileen, can you make the screen bigger?
Okay. I can't make the pop-ups bigger, just the spreadsheet behind it.
This is helpful.
Okay, so now we're going to add some BMPs to the single family land use in the middle example creek. So we want to change this to watershed 2, single family land use. And let's say we're going to do rain barrels here. So we pick rain barrels. This is an LID practice. And what this is a volume control practice. So this is going to have the design capture depth and the amount of impervious. So we're assuming this is 100% impervious because it's rooftops. We're going to leave the runoff capture depth as 0.5, and let's say it treats an acre. So we'll apply this BMP, and it'll give us the percent captured volume from these practices, the BMP storage capacity of those, and the estimated number of units necessary to achieve this. And it will also show you the runoff reduction. You can change this if you have more specific information, but this is what it's been calculated as. So just click OK, and you'll get your confirmation. All right, so now let's do another one. We're going to assume that the institutional land use in the same watershed, watershed 2, has infiltration basins. And we're going to say there are 7.5 acres treated by these practices. And we'll say that it's 65% impervious in this area. We can also change the runoff capture depth. Let's say that these are designed for 1.2 inches. This is also a volume control BMP, so the percent volume captured, storage capacity, and the required BMP area to meet the capture depth are provided. Show that here. And you get a confirmation. So table 4 is summarizing all of the loads before our BMPs, the load reductions from those BMPs, and then the resulting loads after the BMPs are applied. And table 5 will show you your captured flow volume from your various practices, and table 6 will give you the acreage or number of practices for those BMPs, the volume BMPs.
Breaking in here again, there has been some discussion about zooming, and it has been noted by people much smarter than myself that GoToWebinar comes with a nice zoom feature on the top. You'll see something that says zoom with some percent on it, and you can make that actual size or change it to whatever works for you. All right, back to our regularly scheduled programming.
Okay, thanks. So we can quickly go through a BMP calculator example if you've got multiple types of urban BMPs within your given urban land use. As I mentioned, you can use the calculator for these, and it works exactly the same way as the others. So let's just do a quick example. All right, so here we have a 1.5 acre commercial parking lot that's been retrofit by replacing 1 acre of concrete pervious pavers. The entire parking lot also has bioretention cells around the edges and in the medians. So we're going to create boxes to represent our pervious pavers and our bioretention. And we'll do an acre for the pervious pavement. And then for the bioretention, we have, this is treating the acre of pervious pavement and an additional 1/2 acre that's not already being treated by the pervious pavement. So what we want to reflect here is the additional acreage not accounted for in the pervious pavement. So that's 1/2 an acre. Hit OK, and then we're going to tie the two together and hit run. And so this will reflect that there are 1.5 acres being treated in total by both practices. And so we can take this and move back to our urban BMP tool, and we'll pick commercial land. Then we'll pick combined BMPs from our drop-down list. And we know it's 1.5 acres. And then here it's going to ask us for our removal efficiencies. So we'll need to get those from our BMP calculator. So we'll just add them quickly. And hit OK. And there you go. So that BMP has been applied. And that's all there is to urban BMPs or creating a combined complex BMP scenario. We can either pause for questions here, or we can jump into the total load tab. Don, do you have an opinion?
No, go ahead with the total load tab.
Just keep going? Okay. All right, I will make it bigger. All right, so at this point, all of your BMPs have been entered, all of your input data has been entered, and we can go to the total load tab where you'll get your results that summarize all of the loads across all the watersheds. Table 1 provides it in aggregate by watershed for your initial load without the BMPs. Then it provides in the purple area the reductions, and then it goes to the loads with the BMPs, and then it gives you a % reduction from your BMPs. Table 2 breaks out your land use loads with the BMPs by the different land uses, but it's in aggregate for the watersheds. So it's aggregated in a different way in each of these. If you need more specific information on a specific land use in a specific watershed, you can unhide the rows between these two tables and see the results for specific land uses in specific watersheds. And then the final tab we have is the graphs. So this provides a visual display of the loading rates, the reductions, and any proportional contributions of loads by land use. This page is locked. You can unlock it by clicking on Review and then Unprotect Sheet, and that will allow you to manipulate these tables or copy and paste as you want. However, there is another option. If we go back to the input tab. At the top here in row 10, there is an export data button. And this will produce a couple of options for you. It can provide you with the outputs only from these tables in the total load tab, or the outputs with the graphs, or inputs and outputs, or inputs and outputs with graphs. You can choose whatever you want. So you just click on whichever one, hit OK, and it's going to create a Word document for you that produces everything that you've selected. It's the exact same information from the total loads and the graphs tabs. It's just in a Word document for you. And you do probably need to do a little formatting to get it to look report ready. Here's an example of what it looks like. So you can see that it does need a little work, but the data's all there and ready to go in any reports you have. We have one last feature to demonstrate. I'll do this real quick. So STEPL provides an option to add user-created BMPs or edit BMP efficiencies for practices that are already in STEPL. If you have good local data, you may want to substitute that for the default values or add your own practices. So we can get there again by going to the STEPL menu, the add-ins, and then we can go to the View Edit BMP list. You can also get there by unhiding the tab for BMP list from the tabs at the bottom here. So you want to insert a row in whatever land use you're working in. And you want to make sure, don't touch the gray rows. You need to have, the gray rows need to stay as they are for STEPL to function. So you would just add your land use type, your BMP name, and then your efficiencies. And if you don't know an efficiency, you want to type ND for no data. Don't leave it blank. You have to type something there, otherwise it won't work. And then you click Update BMP Data, and that will add your BMP to all of the drop-down lists throughout STEPL. It's just processing through all the tables right now. So just remember that efficiencies must always be less than 1, and you have to fill out all the pollutant fields and include the ND if you don't have any data. So as you can see, we just got a confirmation that it was successfully updated. Now, if you want to save your BMPs to use later, you can click Save Updates. However, that is going to permanently overwrite all of the original efficiency values in this spreadsheet and future spreadsheets that you use from here. So you want to make sure, if you want to save the updates, that you don't really need the default values, that you're okay with permanently saving over them. And I think that is about it. We had some conclusion slides, but I think in the interest of time, I'm going to skip that and just leave our contact information and the website up here, and maybe give ourselves 2 or 3 minutes for questions.
Okay, jumping in real quick. Nicole asks, does STEPL calculate E. coli loads and load reductions?
It can if you populate the data. There are currently no E. coli data in here. It's essentially a placeholder. I don't know, Colin or Don, do you have any? Do you want to expand upon that?
Well, I was going to say it can if you wanted to, and talk about, right now we have zeros as placeholders, and so if you have specific BMP efficiencies as they apply to E. coli, you are welcome to use that. E. coli is a little tricky because it's a living organism, so it's not sort of a straightforward, like, sediment or nitrogen and phosphorus where you just kind of remove it. It's a little bit more dynamic, and there are, if you want to get into probably more accurate ways of computing E. coli in the watershed, there are probably more sophisticated models that will do that better. However, I think at a planning tool level, it still has utility. to this day, EPA has not wanted to supply BMP efficiencies associated with E. coli because it is dynamic. So again, it's one of those things we use at your own risk, but I do think there is a place for it. And Colin, do you have anything else you'd like to add?
No,
After
I
you take
mean,
your step?
I think that you covered, where our thoughts are, and at this point, we're really looking into the appropriateness of this tool's use for providing those values, and that's kind of our next on our to-do list. And we'll definitely keep all of you apprised of, what we decide from that kind of look into the tool. And we hear your asks. We just want to make sure that that we're not getting outside of the scope of the appropriateness for this tool.
And I think we have 30 seconds if you want to talk about the future of STEP-L. Some folks have asked if you can use it on a Mac, for example.
Yeah, so we are currently in the process of migrating STEP-L from its spreadsheet version into a version hosted within Grits. The thought behind that is that we won't have to worry about any future updates for Excel or any new Windows updates kind of messing up our tool. Also, it does open up the opportunity for people using different operating systems to kind of use this tool moving forward. So in theory, we'll have a beta coming up here shortly of this Grits hosted STEP-L product. And if you have any interest in being a part of that, please, shoot me an email. And we'll try and get you in on this beta testing.
So cloud-based computing.
We're getting with the times. What can we say,
And I'll leave the last word to Aileen or Mustafa.
I just want to thank everybody for sticking with us. I know it went a little over the planned hour and a half, but there's a lot to cover here. So hopefully for folks that weren't able to stay the whole time, they can watch the recording. Thank you all.
We'll be posting a archived version of this to the STEP-L website at our first opportunity. I imagine it'll be within a week or two.